Hello. Today we're going to be speaking about threats to internal and external validity. This applies primarily to experimental research, but it's also relevant to, any type of cross-sectional research like survey research as well. So just to remind you, I think we looked over this again, but we'll be looking at this in more detail in the next unit on experimental design. But this is design notation. So the X indicates the experimental treatment or the independent variable, or the condition is another word for it. O represents the observations of the dependent variable. So like uh, your testing that you're actually doing. And R represents random assignment to groups. Each group is shown on a separate line. So in the example on this slide, this is a classic experimental design. The R's indicate that first of all, there's two lines, so it's two groups. The R's indicate that the people have been randomly assigned to the experimental or the condition group. We have O's for each, so we've got a pre-test and a post-test. And then the top one obviously has the X, so that's the experimental condition. And the lack of an X on the bottom shows that they didn't get it, so they have to be the control group. We talked about this a little bit already, but we have to really focus on control and experiments. We want to control all aspects of the experimental situation in order to isolate the effects of the treatment, or like the condition, as well as alternative explanations on what could be influencing our dependent variable, our outcome variables. And it's important that we have to think about all these different variables that could be influencing our outcome variables. So there are three necessary conditions for causality. We went over this a little bit already. One is obviously there has to be, if we're looking at the variable A and variable B, saying that variable A is causing variable B. First of all, there has to be a relationship. These things have to be related, the two variables. There also has to be a temporal antecedence condition, meaning that one thing has to happen before the other. So variable A has to happen in time before variable B. And obviously, this is why cross-sectional research can't actually meet the conditions of cause and effect, because it doesn't have this temporal condition. And thirdly, we also have to look at if we've controlled for alternative explanations. Is the relationship between variable A and variable B true, or is it due to other confounding or extraneous variables? So obviously, extraneous variables are anything that can compete with the independent variable in explaining the outcome of a study. Extraneous variables are often called confounding variables. And so these are things that might influence our dependent variable. And they could also influence our independent variable. They can influence both of them as well. So for example, if we were looking at if there's a correlation, a relationship between coffee drinking and the likelihood of a heart attack, we would be justified, we could look at, there is relationship between coffee drinking and heart attack. This has been found in research. But we would also want to look at other variables that could also, be related to coffee drinking and heart attacks. For example, one of these variables would be cigarette smoking. Cigarette smoking is related to both of these variables. The more, and I would say this is a bit of a outdated example, but in the past, coffee drinking was positively related to cigarette smoking, in that the more people drank coffee, the more likely they're going to have more cigarettes. So there's an observed relationship then between coffee drinking and heart attacks, but it could be because of a third variable of smoking. So In order to actually look at the effects of coffee drinking on heart attacks, we would have to control for the effect of smoking in order to determine if this rival or alternative explanation really accounts for the original relationship. So, the way that we control for these alternative explanations is the primary way in experiments is to random assign. So, this is when this isn't totally different from sampling. It is not random sampling, it is random assignment. So, it is when you have your pool of participants and you randomly assign them to either the experimental or the controlled conditions. We could also use deception. Deception is basically when you mislead subjects. You're in a way lying. For example, we use this a lot in drug related research, in that people are given a pharmaceutical drug. It looks exactly the same as the real one, but in this case, it's a placebo. And so that's one thing that we have to look at. Or, for example, like that's a study that's been done in HKR, Dr. Button looked at BioFreeze, the muscle rub, and I can't remember exactly what he was looking at, but it had to do with pain perception and other things. But BioFreeze then sent him a placebo. So it was in the same, tube of muscle cream, looked the same, except it didn't have the active ingredient that's in BioFreeze, which, by the way, is only menthol. So in this case, you're misleading the subject. So in order to really determine the effect of the menthol muscle rub on pain perception in muscles, you have to mislead subjects. And then we also do this through experimental design procedures. Controlling for all the different things. The other day, we talked about my grade 7 science project, where I tried to control for things like the amount of sun, the type of soil, how much water was given, um, who was actually doing the measurements on the plant, like to measure the height and stuff, making sure the same person was doing it. Um, all these different ways of controlling for anything else that could have affected, in this case, the growth of a plant. So just going to review a little bit of reliability and validity. So we went through this the other day, but just to refresh, as it's important to understand for this topic. We know then that reliability is obviously dependability or consistency. It is the same thing as repeated or reoccurs under identical or very similar conditions. In contrast, you can have validity, or which is the truthfulness. So it really is like, are you actually measuring what you want to be measuring? Are you measuring the truth? It is the match between the definition of your variable and how you're measuring it. And we also have external validity. So this is our ability to generalize findings to a specific setting or a group of people or events. So people outside of the experiment itself. Does your experimental results relate actually to the real world? So this can be issues of external validity. Obviously, the sampling technique, if you're using not really random sampling, you're just using a purposeful or haphazard sampling technique, then those people are not really representative of your population that you're studying, so it's not going to generalize very well. It's going to have lower external validity. Also, the location, where the study takes place. We talked about, like, in a laboratory. Uh, laboratories don't necessarily relate to the real world because you're controlling for so many variables and participants are acting differently in the lab. So it's going to have less external validity than if we had done more like a real less controlled experiment. And of course, time, when the study takes place. This could be the time of day, the day of the week, the seasons. For example, if you're investigating physical activity of people in winter months in Newfoundland, that's not really representative of physical activity in a normal situation in another season. In Newfoundland, physical activity levels go down in the winter. So obviously then internal validity is our ability to eliminate all these different explanations that could be influencing the dependent variable. It's really looking at how well you're controlling your experiment, having no other possible errors or alternative explanations. And external validity is our ability to generalize from to specific settings, people, place. So again, we want to make sure that we have good external validity and that our sample, we can take our sample and generalize it back to the population of interest that we're looking at. And unfortunately, the relationship between internal was not unfortunate, it's just a fact. The relationship between internal and external validity is opposite of each other. The more you're controlling for things in your experiment, you'll have a high internal validity, but it also can influence the external validity, and you actually might not be able to generalize back as much to the real world. So again, internal validity is about looking at not having any errors in the design, making sure that all the variables other than the treatment or the condition, the thing that you're manipulating, isn't actually influencing your outcome or dependent variable. And if you do have errors, these types of errors, then that's a threat uh, for you to actually have a cause and effect relationship. Uh, Issues with internal validity, any errors, then it reduces the ability to say that your treatment, your condition, your independent variable was the true cause or causal factor that actually created change in your dependent variable. So there are various threats then to internal validity that we're going to discuss. And each of these is important to look at and think about when you're designing a study, as well as when you're critiquing an experimental study or even a survey study. So I'll be going through each of these individually. So selection bias. Selection bias is, this isn't the same as sample bias. Sample bias is when your sampling technique has created a bias in, the participants that you have selected. Okay, so meaning like it's not randomly selected. You've used non-probability sampling, like purposeful sampling, to recruit your participants. Selection bias is about not having the same people in your experimental and your control groups. So it's when you don't have equivalent groups between the group that that is being manipulated to do the treatment or condition and the group that is the control group that's not receiving that. So it's really, you have to look at, you have selection bias if your control and your experimental groups are not equivalent. They're not the same at the beginning of the study. So this is, again, and this can be, it's really a threat for more, if you have, two group design, if you don't, you do random selection. So the way that we eliminate selection bias is to randomly assign people to the groups. And also you can test for this statistically, like you can run analyses on your experimental and control group, comparing them on, for example, the pre-tests that you do or socio-demographics, so you can actually see if the two groups are fairly equivalent. So that's usually something that is done as part of descriptive statistics in experimental research. But if we have selected our subjects or participants, by random sampling, and we did random assignment, putting, making sure that everyone has an equal chance of being in the experimental or control group, then we have a much better chance of having equal groups that we can compare so that we have equivalent groups. Um, but if we actually allow people to self-select into the experimental or control groups, then obviously this would have a major influence on the dependent variable. And a little bit of kind of a silly example, but for example, if we did a study where our experimental group was, elite athletes, like high ability in terms of physical activity, and our comparison or control group was recreation recreation athletes, like who have a low or moderate ability, then these groups are not equivalent. We can't say then that our experiment, our treatment that we're doing, actually had an effect at all, because the results could simply be due to having selection bias, having elite athletes in our experimental group. Same with, like, if we were comparing, let's say we did a experimental group at the works, like, with at the university, and we were looking at our control group being people going to the YMCA. The YMCA is well, they're both actually nonprofits, but they're going to be different people. People at the works using the works will tend to be have higher income, or at least certainly be more educated, especially in terms of physical activity, compared to people who go to the YMCA are going to be, much more varied in terms of education and socioeconomic status. Another threat to internal validity is called a history effect. So a history effect is an event that is totally unrelated to the treatment or anything that's really going on, but it influences the dependent variable or outcome variable. Um, as an example, uh, if I remember 9/11, so September 11th, World Trade Center attack, there was a large study being done among grade fours in New York area, at least the state of New York. So they were looking at things like how resilient and how much, 9-year-olds cope with different stresses. And then all of a sudden 9/11 happened. Whoops, you know, uh, obviously that was a major stressful event, and it definitely would have affected coping and resiliency and all the other factors that they were looking at of these, grade four kids, 9-year-olds. So, and if I believe in this case too, their treatment, they had a treatment group in one area of the state and, a control group in actual New York City proper. So what that means is obviously 9/11 affected lots of people in the world, but it would have affected people living in New York City. So in that case, it influenced the control group more than it did the experimental or treatment group. So history events, they're more important to look at when it is just one group. So, sorry, if you have only one group in your experiment, one massive group, obviously that event is going to happen for everybody. If you have two groups, it's not as influential because then you can still look at how your condition or your experiment influenced the group. Now, these it's very difficult sometimes to understand history events. Often researchers don't even know things that happened, but it is something that we have to consider, especially, for big things that could be influential. So, for example, if we have one group, that has a pre-post test, or it could be a repeated measures design or a longitudinal design, the effect of the treatment could be is obviously the difference. We look at what is the pre-test scores versus the post-test scores, and we look at the difference between the pre-test and post-test in order to look at, if our experimental treatment worked or not. But we don't know then, if we only have one group, if that difference could actually have been due to some sort of history event. In contrast, if we had two groups, so if we had an experimental group and a control group, this is not going to be as big a deal because the comparison is between the treatment and the control group. So if the history effect occurs for both groups, then the difference is potentially the difference between the groups could be isn't going to be due to the history event. It's going to be due to the treatment or condition. So a couple of other examples would be, let's say you had a very short experiment um, that is to investigate the effect of computer-based instruction. So like online, something to involving computers to learn something. And sorry, SS means subjects. Let's say some of the participants missed some of the instruction because there was a power failure at the school. So we're trying to look at if this computer-based instruction is better for learning, but then the power goes out and they can't use the computers. So this would obviously impact the dependent and outcome variable. Another one would be if we were let's say we were looking at the effectiveness of a smoking cessation program. So that means like a program to help people quit smoking. And we were just doing this, at MUN. And then all of a sudden, there's a major national stop smoking campaign. And it begins, during our experiment. Well, then we don't really know. Was it our smoking cessation program that was effective? Or was it this major national, campaign where people are seeing ads and posters and all that sort of thing? Maturation is also an effect that can influence the internal validity of a study. And so think of it, it's like maturation, mature. So this is when your actual participants have a biological, physiological, or emotional change that is not anything to do with your experiment or the treatment, but it's just simply change over time. This is more of a threat when you have one group because you're not really sure how they've changed, over time, or if that effect is actually more influential. Is it actually interacting with your treatment, or if we have actually two groups, an experimental group and a control group, then we can assume that they might mature at the same rates, and therefore differences are more likely due to our condition. But if we have only one group, we can't really we don't really know then, is it our experiment or condition or independent variable that had the effect, or was it due to maturation? This is more of a threat also for longitudinal designs or experimental. So the longer your experiment is, the more likely that maturation can be an issue. For example, I talked to you about my caregiver study where I had for my dissertation, where I looked at caregivers for over 3 years. So year one, year two, and year three. And obviously there could have been maturation effects in that. Now, in this case, it wasn't that they were growing because they're not children. It was more that they're dematuring, but they're having change in biological and physiological processes. So if you have, again, if you have a two-group design, it's not as big of a deal. So if you have an experiment and a condition, then there's going to be change in groups. We assume they're going to mature at the same rate. But this is an issue for the longer your longitudinal design is, and also for repeated measure designs, maturation can happen. Now, this is obviously more of an impact when you're studying children and older adults because they're actually more likely to change in a short period of time. Whereas, once we get to, well, I would say adolescence as well, but once we get to, young adults and up to, middle adulthood, this is not as an effect because they're not maturing at a very fast rate. But another example would be, here I have the performance of first graders in a learning experiment begins decreasing after 45 minutes because of fatigue. So in this case, there's a maturation effect because the kids are getting tired. They are fatiguing, and therefore we can't, and that's just how they are because they're in first grade. So we don't really know if it is our learning or whatever we're trying to change in them, our experimental condition. We're not really sure if that's the experimental condition or if it's just because first graders get tired after 45 minutes. And I think it's generous that I even said 45. They're more like 20 minutes. Instrumentation is also a threat to internal validity. And by instrument, this is like the measurement that you're using, how you're measuring your dependent variable, or yeah, your dependent variable in an experiment. So, or any other variables that you're measuring, okay? So it could be the actual measurement tool changes, or it could be that the person who is doing the measurement changes. So, for example, it might not even be that the uh, individual changes, who's the researcher collecting the data. It can just be that the researcher is maturing. So, you might be, as a researcher, becoming more skilled at making observations over time while the study is going on. And therefore, because you as a researcher are becoming more skilled, you're actually influencing the outcome variable. Is it really because you're getting better at your measurements, or is it because the um, actual experimental treatment is actually causing a change? We don't know. It could also be that you have different people, different humans actually doing the measurements. For example, it's a total no-no, especially when any test, even kind of an objective test like blood pressure, changes. So if you have two different researchers collecting the data, you don't know then if there can be error then between the researchers and how they are doing a test like blood pressure. It could also be that your equipment changes. For example, if you were measuring people's weight in a study, and your scale um, gets broken, I don't know, something bad happens to the scale, and then you have to buy a new scale to complete the experiment. It is not the exact same scale that you have used from pre-test to post-test or repeated throughout the experiment. Therefore, it is a threat to internal validity. And this does happen sometimes in the lab in kinesiology where equipment breaks and they have to purchase something else in the middle of the study, and it could affect, I'm not saying it would, but it could affect results. And also, if the reliability of an instrument is affected or reduced during a study, it can influence things. So, I don't know, this could be like, the instrument isn't calibrated properly. Um, and so there's some sort of change in it, and it's not as reliable as it once was. So, instrumentation can be a factor. We also have to look at testing and learning effects. So sometimes your pre-test, so before you've actually done the experimental condition, your baseline data, it can affect the outcome variable itself. The pre-test scores could influence the post-test scores. And this is because participants can become aware or sensitized to the measures, and this triggers then a learning effect. As an example, if I was looking at how well, how great of my 6,000 instruction is to helping HKR master students learn quantitative research methods. I might decide I'm going to give all of you in a class a test to evaluate your knowledge of quantitative research methods. I would give you the test on the first day of class as a pretest, and then I would give it to you during the examination period, the exact same test on the as a post test. And then I'm, doing 6,000 class, and so I'm going to then look at the difference between your pre-test and post-test scores to determine how much you have learned. And I'm going to assume if you learned some things, it's because I was such a wonderful instructor. However, by the very fact that I gave you the exam on the very first day of class, that would have triggered your learning. It would have influenced you. You will have done better on the post-test exam because of just regardless of how great of an instructor I was or not, but just because of the fact that you saw the test on the very first day. So it's called, that's a testing effect. And obviously this can also happen a lot, especially with physio like not objective measures, but especially when we're looking at um, things to do with performance in the human body. Even let's say a sit and reach test. Your If you did a sit and reach test as your pre-test and then as your post-test, the person is probably more likely going to do better in the sit and reach test on the at the end of your experiment, regardless of what you did, just because they have been primed to learn. So again, a pretest can sensitize participants in unexpected ways, and their performance on the post-test can be just because they were given a pretest, and it might not have anything to do with the treatment. Or more likely, it's an interaction of the pretest and the treatment. If you only have one group, such as repeated measures design or a really bad experimental design with just one group, it's not a big deal. But it is, I'm sorry, I've just messed that up the wrong way. It is a big deal. If you have one group, you can't really isolate then whether you have a learning effect or not. If you have two groups, though, then you know that both the experimental and the control group are exposed to the pretest. So the difference between the groups is can't be due to testing, because both the experimental and control groups would have had a testing effect. But this is something that can impact a one group or even a repeated measures design. Also, this isn't as much of a threat when the measures are things that a person cannot control their response to, like more of a physiological measure. But whenever there's something that's a performance measure, like knowledge or attitude, or as I said, even something like sit and reach, where, I mean, it is physiological, but the individual can impact their own performance in it, this is when you can have a learning effect occur. We can also have boredom effects. So, a boredom effect is when your participants' performance on measures or tests is affected because you're doing multiple observations or tests or conditions. So, the person just becomes bored with being a research participant. When this boredom occurs, obviously they're not focusing as much, and whatever testing you're doing, their performance on these can be drastically impacted. So boredom effects are more of a concern when you have repeated measures designs because the person is doing the same thing over and over and over again. Um, so anytime, the more observations you do, the more likely people will have boredom effects. And obviously, if we have a one group, only a one group experiment, like a repeated measures design, boredom effects can definitely become an issue. Just like testing effects, though, when we have two group design, like an experiment and a control group, boredom effects are not as important because they're going to be equal between the experiment and control group. So we're going to assume that they all have boredom effects, and that then any difference we see between the experimental and control group is really due to our treatment or independent variable, and not really, it's not due to the boredom. We also have mortality, or attrition. We usually call it attrition, but it's also called mortality. And this is simply when participants leave the study. There can be obviously many reasons why uh, people might leave an experiment. They move, they can't devote the time. Um, it's affecting them somehow, like physically or psychologically, or they die. You saw in my dissertation at year one, I had 311 participants, and in year three, I had, I don't know what it was, 273. And all of that attrition was due to death. So, um, it is obviously losing people affects the study. This is a really big threat if you have two groups. So if you have an experiment and a control group and you have people leaving the study, then your groups are no longer equivalent in terms of size, but also there could be like selection bias is happening again. So we really have to ask ourselves, like, um, how important is attrition then in the study? You got to look at how many people dropped out of the study. Did that actually affect the results? And did the same number of participants make it through the entire study in both experimental and comparison groups or control group? So, for example, if you have two people leave the experimental group and two people leave the control group, that's not as big of a deal. But again, you have to then reevaluate if you have potential selection bias because your groups might not be equivalent anymore. And again, this isn't a threat if you have one group because it doesn't impact it as much. It's when we have multiple groups. But more importantly, attrition can affect statistical validity. So when we have attrition, that obviously influences our sample size. Sample size affects the degrees of freedom that we have, which is influenced by degrees of freedom is about your sample size as well as the number of variables that you are looking at. Degrees of freedom influences statistical power, so like how likely or how strong, more likely we're going to actually see a true effect, and statistical power influences effect size. So this can be very detrimental to studies if you have people dropping out. So how do we solve this? Well, a lot of people will oversample. So for example, if you know that you need 30 people in your experimental group and 30 people in your control group, you might actually oversample, and let's say you might do like 35 people in each group. That way, if you have some people leave, it won't be, as big of a deal. We also work really hard at retention techniques. So this is especially important in very um, longitudinal studies that are happening. Let's say like data collection is happening month one, and then 6 months, and then 12 months, that kind of thing. And it's about continuing to have contact, reporting back to participants about what's going on, making phone calls, emails, all that stuff. You're trying to keep them in the study. So, but attrition can also be about who is more likely to drop out. So, for example, if we were looking at some type of experiment, we're looking at health, and they had to do a bunch of physical activity exercises, who's going to drop out of the study more likely? It's going to be people who find it difficult. So, if you um, and obviously this will impact then our outcome variable, because we don't know then if it is our experiment that worked, or is it because people that found it hard actually just dropped out of the study. Statistical regression is a bit of a hard one to understand perhaps at first, but it's basically an effect that is the result of a tendency for subjects or participants um, that they're selected on the basis of extreme scores. So that people have an extreme score, and when you have people with extreme scores, the average ends up, it regresses towards the mean. So what this means is that, as an example, if someone is kind of an outlier, if they have like the best or the worst score, the likelihood of change between pre-test and post-test is going to be different. For example, in my example where I'm going to see how great of a teacher I am for quantitative research methods, and I gave you, let's say, like a final exam kind of situation, an exam, knowledge exam as a pretest, and then I gave you the knowledge exam as a post-test. Let's say some of you have done a lot of reading outside of, classes, or you've taken more than one undergrad stats course or something like that. You're going to have a really great pretest score. So you're going to have very high knowledge about quantitative research methods. That means that on the post-test, you can't really get that much better. If you get 90% on the pre-test and you got 95% on the post-test, you're only improving by 5%. So it might look like, which means that you're, and this will affect the mean then when we're looking at overall scores of our experimental group. Similarly, there could be someone who has never done research methods, and therefore or statistics, and therefore they are going to have very low knowledge on my pretest. Therefore, they're going to get better really, really a lot. So if you got 40% on my pretest of quantitative research methods knowledge, you get 95% on the post test because you've learned so much. So it's going to look like I've been really great teacher, but maybe it's just because you had more room for improvement. So when the measurement of, when your dependent variable is influenced, the tendency for these extreme scores to regress or move towards the mean can be a factor. And the amount of statistical regression is actually related to the reliability of the test. The more reliable your measurement is, the less likely you will have statistical regression. And apologize, I just said this, what's on this slide. So when you have a very reliable measure, this is not as big of a deal, but if your measurement is not very reliable, you could have extreme scores. And as I already mentioned, it is statistical regression is inversely or negatively related to the reliability of a test. So I kind of gave this example already, but when we have respondents, participants that score really, really well on a knowledge test, on the post test, the average isn't really going to go down very much because those who got a perfect score are more likely to get wrong answers the second time or not change at all. Another example is if we were looking at reading instructions, like helping kids learn how to read. If we had if we were looking at subjects grouped because of poor pretest reading scores, so people who didn't do very well on the pretest reading, they're going to show a lot more learning. They're going to look like they learned a lot. They're going to gain more reading ability than people who scored average or high on the pretest. So statistical regression then is happening because the people who just were not very good in the first place are going to regress more. And this is also why it's good. Sometimes it's a good idea, if like this can be related to sample or selection bias, making sure that you have fairly equivalent groups. You can also have diffusion of treatment or contamination. I spoke of this briefly the other day, but this is when you have a treatment group and a control group, and they somehow communicate with each other or influence each other. So, um, if the comparison group knew or found out about the experimental group, for example, I don't know how this would happen, but if you're in a drug study and you find out that you're actually in the placebo group, that's going to totally impact and influence all of the dependent variables, the outcome variables. And also, it could be that there could be someone who wants to make the research succeed or fail. This can impact if they're, being biased. So often, what we do is researchers will interview participants after the experiment to make sure that there was no design contamination that occurred. And by the way, this is very important in HKR. I have at least seen one experiment where it was supposed to be experiment and control group, and they were supposed to be blinded, meaning they didn't know if they were in the experiment or control group. But they somehow, because it was a master student doing the study, and the master students were the participants in the study, all of a sudden everyone knew if they were in the experiment or control group. So that's massive contamination of the study, because as soon as someone is no longer blinded, then it's going to impact, their responses to the dependent variable. So, for example, if I had a leisure education program, which by the way is it's kind of a program that would tell people about how to have leisure, its benefits, barriers, how to overcome barriers, all this kind of stuff. If I was doing this type of education program to my treatment, my experimental group, and they ended up talking to my control group who wasn't receiving that education program, then obviously my experiment we can be contaminated. So, um, also in an expectancy experiment, so this is when people need to have like knowledge of what they're expecting. It could be that the students were talking to each other, comparing notes about what they were told to expect. So anytime you have people in your experimental group or your control group talking to each other about the study, this can impact results. And also, if, as I said, participants knowing if there's a deception involved, like a placebo, if the participants somehow learn, which group they're in, if they're getting the placebo or not, this would also impact. The sort of related thing is experimenter expectancy. So this is the bias of the researcher. We as researchers are all have biases. We have expectations of what is going to happen. No matter how much you try to be unbiased in research, it is still going to come out. So the way that we control for this in an experiment or reduce the impact of the experimenter expectancy on the outcome variable is to have a double blind experiment. So this is when the researcher and the uh, experiment, like the subject, that you don't know if they're in the experimental or control group. So the researcher is blinded to what's going on. So when they make their measurements, there's no bias involved. Interestingly, I just heard a study where it was very difficult to control for bias or experimenter expectancy. There's been a lot of research going on right now looking at the effects of like hallucinogenic mushrooms and that type of thing on mental health outcomes. And I was listening to a podcast about this, and it was interesting. The researcher said one of the biggest problems is that he can't actually double blind because no matter how much he controls, in the environment and controls for everything he possibly can, when he's observing the participants, some are actually given the hallucinogenic and others are given a placebo. Obviously, you can tell if someone is having an hallucinogenic. So he knows, even though it is, there's a an actual drug and there's a placebo, he as a researcher knows which one the participants got. So he cannot, due to the nature of the drug that they're studying, he is not able to actually fully control for experimenter expectancy. We can also have statistical lack of statistical validity. So obviously this can impact the internal validity of a study. So this could be things like fudging the data. People might um, change a couple data points, do a little this or that, change a missing data point to be the mean of the whole sample. All these types of things. They're actually, we call this, it's kind of lying. It's fudging the data, manipulating your data improperly. Statistical fishing is also quite common, and it also is massively an issue to internal validity of studies and to, in my opinion, the integrity of research in general. But a lot of times people collect data and then they run a whole bunch of tests, zillions of different statistical tests that they can do. And then when they find the one test that actually shows a statistically significant result, then that's the one that they write up their whole article about. So it's basically like they call it statistical, like it's fishing, because it's basically like, you're actually fishing and you catch a little goldfish, a little goldfish, a little goldfish. Finally, you catch a big mouth bass, and then you only write about the big mouth bass in your results. So you're basically doing a whole bunch of analysis just to find the one um, analysis that's what you want, that's going to show a statistically significant result. Again, this is, I mean, it's about ethics as well in this case. It's not ethical to do that. I've spoken about this already, but also not using the correct statistical model for the data is can affect statistical validity. For example, if you use a parametric test on data that isn't actually normally distributed, that would be a factor. And another big factor that influences statistical validity is having low sample sizes. The lower your sample size, the lower the statistical power, and therefore you're going to also get low effect sizes. That was all the different threats to internal validity. So looking at how controlling for all the different possible explanations or variables that could actually impact the outcome or the dependent variable. When we're looking at threats to external validity, one of the biggest things then is the population validity, or your ability to generalize your sample to a population. So we have to look at things like how representative is our sample to the actual population that we're trying to study. The more similar it is, the more representative it is, the more confident we can be that we can generalize our sample to the population. We also have to look at how widely does the finding apply. If it's just like this very, very unique sample that we looked at, then it's not going to be able to generalize to the broader population. So generalizing across populations occurs when a particular research finding works across many different kinds of people, even those that are not represented in your sample. We also have to look at ecological validity. So ecological validity is basically, like how strong is your ability to generalize across settings. So think of ecological is about like ecosystems, okay? So ecological validity is, for example, If we did a study in Newfoundland, is it going to generalize to other provinces across Canada? Um, if we, uh, for example, only studied 20 to 25-year-olds, um, does that actually translate to older populations? I don't know. So you really have to look at the greater your ecological validity, the more likely you can say that this is a true effect across a whole bunch of settings or populations. And ecological validity can be impacted then by the interaction effect of testing. So we'll talk about that in a second. Interaction effects of selection bias and experimental treatment. And finally, multiple treatment interference. So the interaction effect of testing is when your pre-testing interacts with your experimental treatment. And this causes some effects such that the results are not going to generalize to an untested population. For example, if I was looking at some sort of physical performance, and that was my main outcome variable, I'm looking at how well is someone physically performing on some measure. That pretest, we've talked about how pretest can impact the outcome variable. The pretest is going to prime or trigger the participants to respond in a certain way to that experimental condition that would not have happened if I never had done a pretest. So this can then impact our external validity because maybe, like in the real world, we're not going to do a pretest. So if a pretest is having that big of an influence on the outcome variable, then it's going to be reducing the ecological validity, or the external validity of our study. We can also have interaction effects of selection bias and experimental treatment. So there could be, remember, selection bias is when you don't have equivalent groups, when your experimental and your control group are not the same. They have, they're not equivalent. So if you have an effect of some selection factor of a group, it can that's interacting with the experimental treatment, it could be that would not be the case if the groups have been randomly selected. So what this means is if you have selection bias, you don't know that it actually impacted, that it was your experiment that actually impacted the outcome variable. It could have been the inherent selection bias of your group. Maybe that was what was actually affecting the outcome variable. So this is again why it's so selection bias can not only impact internal validity, but it can also impact um, external validity. And this is why randomly assigning people to control or experimental groups is very important. So an example is if the results of an experiment in which a teaching method is the condition, is the thing that we're doing it, if we like had a class of people who were not very motivated, low achievers I have here, our experiment isn't then going to generalize to just a normal set of students because we're only looking at low achievers. We're not looking at middle or high achievers. So we really don't know that our teaching method actually had an impact. It could just be because we had low achievers, we had selection bias to begin with. I spoke about reactivity earlier. So reactivity, or sometimes is called the Hawthorne effect. It's simply that participants can act differently just because they're in the study. So it might not be anything to do with how they would act in the real world or normal, but they are changing their behaviors because they are actually in a study. So you're reacting to being observed. And obviously, this then impacts external validity because the participants aren't aren't behaving the same as they would in the real world or if they hadn't been in the study itself. So, a couple of examples. This could be like exercise testing. People generally will perform better on any type of exercise testing because the researcher is watching them. um, People act, and they've even done studies on this. They have someone in the room watching the participant and then not have them in the room, um, which you can't do ethically in case something happened. But, they're able to look at these things and see that, people will usually exert more effort into something because the researcher is watching them. Another example would be a remedial reading instruction. So remedial means like low level or basic reading. So looking at people who really need help in their reading, children. So an experiment in remedial reading instruction could have an effect that does not occur when the remedial reading program is implemented into the regular program, meaning that the kids are in this special program, so they're really working hard on their reading. And when that reading program is just integrated into the normal classroom, the kids aren't going to try as much because they're no longer, actually being observed or as part of a special program. Um, this happens in drug studies. People can act differently, report positive effects of receiving a treatment like a drug just because they know they're receiving that drug. So, and again, this is why we blind participants so they don't know if they're receiving the drug or the placebo. And we'll talk about this later, but placebo effects are very strong. Placebo effect can actually count for like 30% of what's in an outcome variable. So, and so placebo actually isn't a bad thing, like, especially if it is positive for your health. So you're taking like a supplement that actually isn't doing anything and you feel like it's helping you. Well, that's okay as long as the supplement's not hurting you. But when we're actually looking to see how effective that supplement is, we want to make sure that people then are blinded. They shouldn't know whether they're receiving the placebo or the actual drug. And finally, when you have a whole bunch of different treatments, it can influence the external validity of a study. So this is called a dose effect. So this is very important to repeated measures. So when the same person, the same participant is receiving two or more treatments as repeated measures design, there can be a carryover effect between treatments. So you could have a carryover effect that is influencing the next or the preceding condition or treatment. It might not have anything to do with that treatment itself. It can be a combination of, which came first. So, for example, in a drug experiment, the let's say we're looking at drugs with some animals, and we're giving them four different drug doses. So, like a low, medium, high, and very high. We don't know then if the effects of the second to fourth doses are actually because those doses worked better, or if it's a delayed effect. It could be that the first dose you gave them has created a change in the body that is then impacting how the body is reacting to the second, third, or fourth doses. And that concludes my discussion today about threats to internal and external validity. Everything that I've presented in this video then is the knowledge that you need to do your journal article critique 2, where you're going to be finding an article of your choice, preferably a study that is related to either your major stats assignment, like the big written assignment we're doing in this course, or to your thesis, and you're going to evaluate all the different threats to internal and external validity, that could be influential. This is a table that you're going to fill out, and you also need to provide citations to back up your sources if possible. And if something is a threat, I want you really to focus on how would you have improved or controlled for that threat in the experiment. How could they have improved this limitation so, it wasn't a limitation of their study. All right, take care, and next week we'll be looking how do we compare two means.